All right, chemists, let's get started. Only 3 more lectures left. So I promised you on Monday that I'd post the resources for the final exam. So I do have that posted. It's not quite complete yet, but there's a lot of new material for you to study from. So I'll just walk you through it here. The page is at the very top of the lecture module. It's the first thing you see when you click on modules because it's that important. This is the final countdown. So a lot of the questions you may have, in your head right now are answered here. The final exam is around 50 to 55 questions. All chapters are covered equally. It's the same format as previous midterms. So like pull down, numerical response, multiple choice, all that stuff. Our final exam will be in this room during the university scheduled time for our class meeting time. And so that's in the syllabus. You can also find it in Buckeye Link. It should show up on your schedule, but it is in this room. And so it's Monday at 8 p.m. That's crazy long, crazy late. So 8 p.m. And you're given an hour and 45 minutes. So 105 minutes instead of the 70 minutes. So do review the makeup policy. We had a very, very lenient midterm makeup policy where you could make up a midterm at the end of the term with no penalty. But in order to get everyone's final letter grades in on time, we will put a penalty on missing the final exam. If you miss our scheduled final exam, you will have a penalty if you don't have a proper documentation there. So do review the policy, all right? So do make it a priority to have that time in your calendar. And so if you do have a conflict, which you shouldn't in terms of exams, but if something does come up, there's a different page for the final exam makeup policy. It's right there. Also, quick note about SLDS. If you do take the exam with SLDS, you need to schedule your test taking time as soon as possible. And it has to be the exact same day as your actual final exam. So on Monday, you have to schedule it on Monday. If you take exams with SLDS, you might be aware of the 3-day window. That is not in place for the final exam. That's an SLDS policy, not ours. So do be aware of that. Don't delay. Their spots do fill up there. So all the same information on this page as you typically see, the learning objectives. Here's the scratch paper you'll get. It looks very similar of previous chapter or previous midterms. I did get an email from our exam coordinator. They decided to add more equations to give you for the scratch paper, but it's too late to reprint them. So we will give them to you at the beginning of the final exam. So things like Avogadro. So do note that even though it's not on that exact piece of scratch paper, you will get Avogadro's number, the ideal gas law equation, they're giving you PIV-NERT. I don't know why, because you should know PIV-NERT, right? PV equals nRT, right? I don't know why they're giving that to you, but they're giving you the 2 different R's we've talked about. So do know that you'll be getting that too. It just didn't make it on the final print version. And so I explained that there. Do test your Respondus lockdown browser again. Yeah. And so I wanted to show you, I have it broken up into new study material, so brand new things you haven't seen before, and all the older stuff. Remember, this is a cumulative final, so you can absolutely use older study materials for chapters 1 through 9. I would really urge you to do that to freshen up on some of those concepts since everything is assessed equally. So right now, the department has not posted their Carmen practice exam, but I've been told that they will sometime this week. It'll show up on this page once it's out. But I already have at least one problem set posted here, and I am writing another one right now as we speak. Tons of problems. So this problem set, it's not a exam, it's not a final exam, it's just a compilation of 70 questions. So it's not timed at all. It's just comprehensive, so you can use this in your studies. Yeah. I already did. Yes, I already did. So when I placed all of so the question is, can you retake the Carmen practice exams? Yes, I just did like yesterday or something. I didn't reset them. I made it so you can take unlimited attempts. That's what I did. So I think you have to like click some buttons to do it again. But I would urge you to look at many questions as possible. Like, don't take the same practice midterm 5 times in a row, like hoping to get like 100% by the end. No, like you want to look at as many problems as possible, right? And experience like different ways to ask those questions. So, older study materials, yes, you can use these old pages. Here are my old practice paper midterms, previous Zoom sessions, and all the overview sheets for each of the chapters, and the recitation packets. You ever write the same word over and over and over again so much that it's like it doesn't seem like a word anymore? That's what I feel about the word key. Key, because it's like everywhere, right? It doesn't feel like a word anymore. So tons of places for you to practice. Like, I don't want you to put this off and be like, oh, Dr. N hasn't posted the page yet, I won't study yet. No, you want to be reviewing these things now, because I don't want you to get to the review session on reading day and I say, which experiment was responsible for dismantling the plum pudding model, and you blank. Do we know? Rutherford, yes, Rutherford, yes, because he shot things, he shot alpha particles at a thin foil. Most of them went through, but what was the crazy thing that happened? Some of them shot off, meaning that there was a dense nucleus. So that's how we went from the plum pudding model to the nuclear model. So do review those things, okay? Because I don't want you to be saying, oh crap, on reading day. So there they are. Okie dokie. And I will post another problem set. It is in the works right now. I'm at like 120 questions right now. It'll probably be more than that, and I'll post that sometime soon. Okay, so let's move on to chapter 11. What the heck? There we go. All right, chapter 11. So we left off talking about intermolecular forces. All right, let me just go back here to all of our different intermolecular forces. So we talk about 4 different intermolecular forces. These are attractions between molecules. These attractions are responsible for a lot of the properties that we see. I've been told by students, they're like, oh, chapters like 11 and 12, they're a lot more interesting. And I think it's more interesting because we're taking concepts we've learned in previous chapters that were just very out there, very theoretical, but now we're actually relating it to things that we see. Properties that we can see, things that we can measure. So intermolecular forces are attractions between molecules, and that's often the confusion, the mix-up. We spent 2 months talking about bonds between atoms, like covalent bonds, ionic bonds. That's not what we're talking about anymore. We're talking about attractions between molecules. So, oh my gosh, what is happening to my thing? Give me 1 second. My pen's not working. There we go. All right. So we spent like a month talking about bonds between atoms. Between this hydrogen and a chlorine, that's a covalent bond. Right? We can use valence bond theory to describe that. Now, in chapter 11, we're talking about, okay, what's happening between neighboring molecules. So there's 4 different types: London dispersion, dipole-dipole, hydrogen bonding, and ion dipole. So the first one is the weakest, London dispersion. Very important in nonpolar compounds because that's the only attraction that's present in nonpolar compounds. We typically look at molar mass or surface area. Next, we look at dipole-dipole attractions. These are between things that have permanent dipoles, so polar molecules. That's what you want to look for. Hydrogen bonding, that's where we're on now. Hydrogen bonding has a very special criteria, and that criteria makes for a very, very strong dipole-dipole interaction. So that's what I have here. Hydrogen bonding is just a very strong dipole-dipole interaction. These are the criteria. A common misconception is students will think, oh, hydrogen bonding can occur between any hydrogen atom. That's not true. The hydrogen needs to be attached to something very special, right? In order for hydrogen bonding to occur, hydrogen has to be made very electropositive. That happens by attaching that hydrogen covalently to a very electronegative atom, such as oxygen, nitrogen, or fluorine. And then the second criteria is that those electronegative atoms need to have a lone pair on them. They have to. All right, and so by doing this, that's what I have right here. This is what you want to look for: hydrogen attached to oxygen, nitrogen, or fluorine. Any compound that has these, what we call functional groups on them, can hydrogen bond. And so the idea here is hydrogen bonding is responsible for a lot of the biological zipping that structure that we see. So hydrogen bonding is responsible for the zipping up of our DNA. So the DNA strands are held together by specific hydrogen bonding. Hydrogen bonding is so strong it keeps it together, but it's not so strong that you can't unzip it, right? Because in order for DNA to be replicated, doesn't it have to, like, you tell me, I don't know, it has to come together as a strand and then unzip, go do the translation and all that stuff, right? So it has to be strong enough to stay together, but not so strong enough that it can't be unzipped for replication. And the idea here is when we talk about nucleic acids, or the nucleosides that hold together, right, our DNA and RNA strands, what are the different names? There's like U and T and A and C. And your bio person never tell you, oh, U always goes with C. Or no, T, sorry. U always goes with T. And you just go yes, right? And you never think why. Or they say, oh, A always goes with, which one? Wait, which one? A, T, C, G. Okay, so I got it wrong. Sorry. Okay, so wait, C goes with which one? G, okay, yeah. So C, what does that stand for? Cytosine. And then G is guanine. Okay, those two go together, and you just look at your bio person, you're like, yes. That's what you say? Yeah. Okay, so those two go together because the regions where they hydrogen bond are in the right configuration for them to lock together. Where there's two places to hydrogen and they lock together. Versus, so C and G, and then what's the other one? A and T? Yeah, those ones have like 3 hydrogen bonds, all right? That just lock together, all right? And so when we can't like mix them up because the arrangement's not there to have strong hydrogen bonding, all right? So that's why C always goes with G and etc. All right, it's because of hydrogen bonding. Okay, there we go. Also, hydrogen bonding is responsible for a lot of the tertiary structure, of like protein folding and all of that. Strong enough to like fold proteins, and you see, different like beta-pleated sheets and all of that. Has to do with hydrogen bonding that's happening intramolecularly in these long, really large protein strands. So hydrogen bonding, very important. So what you want to look for are these OH groups with lone pairs, or nitrogen groups with lone pairs, which we oftentimes see on proteins. You won't see fluorines in our body very often. So it's oxygen and nitrogen you'll oftentimes see. So let's put this into practice. Let's consider 2 isomers. Let's remember what isomer means. Okay, back to chapter 2. Remember the 2 important things for our secret to chemistry: composition and structure. Isomers share what? Which one? Composition or structure? Composition, yes. So these 2 molecules I'm showing you have the same composition. You can count, you can take inventory. They have the same carbons, hydrogen, oxygens, but they have different structures. Their connectivity is different. So they are isomers. All right, so I tell you the boiling points here. There we go. Based upon the boiling point temperatures, which substance do you predict to have more IMFs present, just based upon boiling points? Propanol or ether? Propanol, yes, it has the higher boiling point. So you got to give more energy to break all those IMFs. So that means there's more IMFs present there. But let's just check our work. So let's look at both molecules. Do they both exhibit LDF, London dispersion? Yeah, because they both are matter, they both have mass, and more specifically, they have the same LDF because their molar masses are the same. They should be the same, right? Because they're isomers. They have the same chemical formula. What about dipole-dipole? Do they exhibit dipole-dipole? I don't know. Look closely at the molecule. There's a hint there. Do you see the thing right here? What's that? That's a dipole arrow. Yeah, so they are both polar, so they both have dipole-dipole, and their arrows, the magnitudes of their arrows are about the same, right? Crap. So we just went through LDF, dipole-dipole. It seems like they have the same attractions, but what did we just talk about in the previous slide? Hydrogen bonding. So let's inspect hydrogen bonding. Can propanol hydrogen bond? Yes, so this hydrogen is attached to an electronegative oxygen that has lone pairs. So yes, propanol can hydrogen bond. Can the other one hydrogen bond? No, it can't. But Dr. N, it has hydrogens. It has hydrogens on it. Can it hydrogen bond? And it has an oxygen. No, it can't, because the hydrogens need to be directly attached to that electronegative oxygen. All of the hydrogens in this example are actually attached to carbon, and so that doesn't fit our criteria. So we see 3 IMFs is greater than 2 IMFs, so that means propanol is going to have the higher boiling point. Cool? Okay, let's do the next one. This one's tricky. Which substance can participate in hydrogen bonding? Or can both of them? You can't just look at this and know. We probably have to draw the Lewis structure. Crap. All right. So let's draw the Lewis structure. NH3, do we know what that looks like at this point? Yeah, it's 3 bonds, but what's on nitrogen? We have what on nitrogen? A lone pair, yes. You don't have to memorize that. You can go through the 6 steps. I'm just lazy. Okay. What about NH4 plus? What does that look like? There's, I think, a total of 8 valence electrons we need to place, so it's N with 4 hydrogens attached to it. Are there any lone pairs on that central nitrogen? No, there's not, so it's just plus. Okay, so based upon those 2 Lewis structures and our criteria, which one can hydrogen bond? Ammonia or ammonium? Ammonia, yeah, so the first one. That one can hydrogen bond because it has the lone pair. Ammonium actually cannot hydrogen bond because there is no lone pair. But ammonium can participate in other IMFs we'll talk about later, so it's not left out. But it cannot hydrogen bond. So it's weird, you know, it's very easy to just like look at these 2 things and be like, oh, nitrogen, hydrogen, great. There's a hydrogen bond. But no, we actually have to kind of inspect their Lewis structures and see the idea of those lone pairs there. Okay, good? Good. That one's a trick one. Like, let me show you another tricky one. So let's see, which picture correctly identifies hydrogen bonding interaction? So the red lines, we want to pick the picture where all of the red lines show hydrogen bonding interaction. So we have a mixture of water. Hopefully by this point you know what water looks like. We have water, and we have hydrogen molecule, hydrogen gas there. So which picture are the red lines only depicting hydrogen bonds? So take a minute, don't say the first thing in your mind, and then whisper to someone near you what you think it is. Do we know which one it isn't? Which one is it not? Like, which one can you eliminate right away? B. B. Hopefully you can see that we can just straight up eliminate B. Okay. Okay, you can whisper it to me. So why do we think B is incorrect? What's circled? These are covalent bonds, right? It's describing these are the bonds holding the molecule together. That's not what chapter 11 is about. Chapter 11 is about the attractions holding molecules close to one another, right? Not the bonds holding the molecule like together, but what's holding our sample together. Attractions between different molecules. So B is not correct, right? Those are like the covalent bonds in the molecule. Okay, so what's the dang difference between A and C? Look very closely. Look at the red line. then look at what molecule does the hydrogen originate from? Then look at the other side of the red line and be like, okay, where does that oxygen originate from? And see if that fits our criteria of hydrogen bonding. So let's look at that bond right there. Right there. So let's look at the oxygen. Is that oxygen electronegative? Yeah, it is. Yeah, it has lone pairs on it. Yeah, but let's look at the hydrogen on the other side. Is that hydrogen really electropositive? Does it fit our criteria from like 2 slides ago? No, it doesn't, because this hydrogen originates from our nonpolar hydrogen molecule. We need our red line to point to an oxygen atom and a hydrogen on a different water molecule. That's what we want to be pointing to. So this is not a hydrogen bond interaction. That's not a hydrogen bond interaction because the hydrogen that's involved here is just a not electropositive hydrogen. It's just like a regular hydrogen. All right. So if we look at C, C is the correct answer. Who said C? In your mind, you can raise your hand. Yes, that C is the correct answer because this is the only one where all of the lines are pointing to a very electropositive hydrogen on a water molecule and a very electronegative oxygen on another water molecule. That's the only one that is showing that. All right, all of these lines right there. All right, and so the idea is this picture is not showing the lone pairs on the water, but those should be implied. And so another reason B, you might be confused about B, you might think, oh, but in B, it's showing like the electronegative oxygen and the electropositive hydrogen, but the problem is it's on the same molecule. It needs to be on different unique molecules. So C is our right answer. Good? Yes. All right, let's do, the last one. Okay, so that was hydrogen bonding, our strongest one. You want to look for OH, NH, or FH groups. Okay, here is the last intermolecular force, and this one's different. This one's like the black sheep, but I like this intermolecular force. So this last one is the strongest, but typically we want to look for salts that are dissolved in water, so aqueous salts. So this one is like in its own class. Dipole, London dispersion, and hydrogen bonding, we typically looked at one pure substance, but ion dipole, we're always looking at a mixture. Typically it's a salt dissolved in water. Because let's break down the name. In dipole, we needed 2 molecules that were what? To interact. They had to be polar. So 2 polar molecules, we had 2 dipoles interacting to have dipole-dipole interaction. So what do we need in ion dipole? We need something that is a ion and something that has a dipole, yes, so it literally is in the name. We need something that has a full-blown positive or negative charge. We need something that is polar, right? So something that's polar with a permanent dipole, something with a dipole moment. That's what we're looking for. So when we think about salt, aqueous salt, or let me say something even simpler, NaCl aqueous. What is that? What do we call that on the street? Salt water. We call that salt water. Okay. If you wanted to make salt water, what would it contain? What would you mix together? Salt and water. So we have a mixture. So let's think about that salt. NaCl, when you name that sodium chloride, what kind of naming rules do you use? Ionic. So NaCl is made up of ions. Okay. So salt water has salt and water. So the other component is water. Does that have a permanent dipole? Water? Yes, it is polar. So salt water contains our 2 criteria. Something that's ionic, salt, something with a dipole, water. So let me show you why this is important, right? We know salt dissolves in water, okay? So let me pose this to you. In biology, who's taking biology? Who's taking biology? Okay, whatever, doesn't matter. Have you ever heard the phrase, like dissolves like? You ever hear that? You ever hear that? Like dissolves like, never heard it. That polar solvents dissolve polar things. Like water. Water will dissolve polar things. Non-polar solvents will dissolve non-polar things. Okay. You'll learn more about it in 1220, and then I will dismantle it all and tell you it's all wrong, actually. Right? So I'm going to give you a little glimpse to it right now. So for the people who have heard the term like dissolves like, does salt dissolve in water? What does your intuition say? No, just like your basic living experience says, yes, salt dissolves in water. Does salt look anything like water? No, salt is ionic, water is molecular. So in your mind, you should be thinking, dang you, bio teacher, you screwed me up. But the reason salt dissolves in water is actually because of very strong ion dipole attractions. When we dissolve salt in water, NaCl, do those NaCl ions stay together? Okay, let's go back to chapter 4 and electrolytes. What kind of electrolyte is NaCl aqueous? Strong. So all of those Na pluses separate from Cl minuses, all right? They're free. So when I write NaCl aqueous, what I actually mean is that we have free sodium pluses and free chloride minuses. But back in chapter 4, I lied to you a little bit. Those ions don't just swim around freely in water. Water molecules are actually what we call solvating all of those ions. Because let's think about it. Sodium is positively charged, right? It's positively charged. So we don't just have this free positive charge floating around. We have a bunch of water molecules that have permanent dipoles on them. So what's going to happen is that the negative butts on the water molecules are going to orient themselves to the positive part of the sodiums, what we call solvating it. All right, so that's the solvation sphere around sodium. Will the negative butts be attracted to the chloride minus? No, waters are still attracted to it, it's just the opposite way. So the positive parts of water are attracted to the chlorides. So this attraction, these dotted lines are our ion dipole attractions, and it's very, very strong. This is super strong. Strong enough to be able to break the lattice energy that is keeping NaCl together in the solid phase. Ion dipole is super, super strong. Okay, so that's where it's coming from. And again, the name gives it away what's needed, something with that's ionic and something with a dipole like water. And that's the best example. All right, so the trends are a little bit different here, and I like to relate it to things we already know. All right, so remember solubility rules in chapter 4? You remember those? Do you remember how to read this table? No? The top of the table, these are things that are really soluble in water, with some exceptions. Things with these anions are not so soluble in water. They typically get the solid designation in net ionic equations, and there are some exceptions. Okay, I just gave you this table and you believed me, right? You believed me. But now I'll show you why this table is made this way, all right? There's some trends here. According to this table, which of these three substances has the poorest solubility? Meaning, which one is insoluble in water of those three? Can you read that? Which one? Is calcium chloride soluble in water? Yes. Is iron sulfide soluble in water? No. Is sodium nitrate soluble in water? Yes. So iron sulfide has the poorest solubility. Poorest solubility. Okay, let's review chapter 8. Of these, the same three compounds, which one has the strongest lattice energy? Which one has the most attractions, keeping the ions together in the solid phase? When we talk about lattice energy, what do you look at? Charges and then size. So let's look at charges. Calcium chloride is +2 - 1. Iron sulfide is +2 - 2, and then sodium nitrate is +2, nope, +1, -1. So which one has the largest lattice energy? Iron sulfide, yeah. So if it has the strongest lattice energy, it takes the most energy to rip apart those ions, all right? So much that the ion dipoles with iron sulfide, it's not strong enough to solubilize, to turn iron 2 plus and sulfide 2 minus into solvated ions, that we can't dissolve it because its lattice energy is so strong. Versus calcium chloride and sodium nitrate have smaller lattice energies, enough where ion dipoles can break it. Does that make sense? Right. So that's why we see a lot of higher charged things in the insoluble side of the table, because their lattice energies of those solids are so strong. And ion dipole is not strong enough to break those ionic attractions and make new bonds. All right, so those trends are a little bit different. I told you ion dipole is it's like the black sheep of all three of these. It's really only important in ionic solutions, so it's a little bit different. All right, so that's basically it. This is the summary of all the IMFs. All right, so take a picture of that, or I don't know, but we already talked about all of these things. All right, London dispersion, important in non-polar compounds, trends with molar mass, dipole-dipole, you need to have something with a permanent dipole, trends with dipole moment, hydrogen bonding are special cases, all right? And then finally, ion dipole, this is the black sheep one. You need some ionic substance dissolved in a polar solvent. Usually it's water. This will be covered more in 1220. All right, but it explains our solubility rules we talked about. All right, so there's the summary. We already talked about all these things. All right, and I like this chart. This one's in your book as well. It shows the same, what's the criteria for each of the 4 different types we've talked about, but I like this because it shows the relative strengths of all of them, all of these different IMFs. So I like numbers, so you can see hydrogen bonding is just like a really, really strong dipole-dipole interaction, and dispersion is the weakest amongst all of them. Okay, so let's do some examples. So we want to determine what IMFs are present in these different samples. So when I say water, I mean a sample of water, tons of water molecules all together. What kinds of attractions are happening in that sample? So, does water experience dispersion? Yes, that's a trick question because everything experiences dispersion. So I can just go ahead and circle everything has dispersion, okay? Everything. But dispersion is usually only important in what kind of substances? Non-polar, because non-polar substances only have dispersion. Because what we'll see here is water polar or non-polar? Polar, yeah, so it experiences dipole-dipole. So up here I'm gonna just write dipole-dipole. We're looking for polar molecules. That's what we wanna ask ourselves. And then if it's polar, ask yourself, does it have the criteria for hydrogen bonding? Does water have that? Yes, it does. So it might help to draw the structure, all right? Because in the formula, it's not obvious that there's lone pairs on the oxygen. You can only get that from the Lewis structure. Does water have ion dipole? Break down the name. Water has a dipole, but are there ions? No, there's not. So no ion dipole. Okay, there we go. All right, CF4. So again, you might want to draw the Lewis structure. CF4 is tetrahedral. There's just 4 fluorine bonds. But what is the polarity of CF4? Polar or nonpolar? Nonpolar, yes, because all those fluorines are identical. All right, so it's like 4 bodybuilders all pulling at the same time. So does CF4 exhibit dipole-dipole? No, because it's nonpolar, so you can literally just not look at anything else. You don't have to look at anything else. Okay. What about C2F2? So it's the same tetrahedral carbon, but it's not, they're not all equivalent now. And so do remember that this carbon is in a tetrahedral sphere. All right, because if I drew it flat and I drew these hydrogens and fluorines are, you might accidentally think that this is non-polar. It is absolutely polar. These 2 hydrogens are on 2 sides, fluorines are on the other side. If you do the babies and bodybuilders thing, you'll see that this molecule moves in space when all the bond dipoles kind of, go at the same time. So H2F2 is absolutely polar. So it does exhibit dipole-dipole attractions when you have a full sample of it. Can it hydrogen bond? No. But Dr. N, there's hydrogens. And there's fluorines. But are those hydrogens and fluorines bonded to one another? No, they're not. So it cannot hydrogen bond. And then it can't ion dipole because there's no ions. All right. C3H8. Does anyone know what that is? That was from chapter 2. It's one of our hydrocarbons, one that you had to memorize. Yeah, it's propane. It's propane. Yes, it came to you, right? Because usually I ask, what is propane? And then you go, okay, 3 carbons, and you put in the hydrogens, right? So it's hard. It's a little harder this way. So yes, this is propane. 3 carbons in a row and a bunch of hydrogens. Is that polar or nonpolar? Nonpolar. All hydrocarbons are nonpolar. So does it exhibit dipole-dipole? No, and so no hydrogen bonding, no ion dipole. So fun fact, so all hydrocarbons are nonpolar. Remember my axiom, like dissolves like? Remember that? It is true like most of the time. So water is polar. When we wash our hands, water is most likely to dissolve what kind of polarity substances? Polar, yes. Yes. See, there's a problem. Have you ever like worked on your car and gotten a ton of grease on your hands? Does water wash that off very well? No, it doesn't. No, it doesn't. Because grease is nonpolar and water is polar. So if you ever talk to your grandparents or maybe your parents, they might say something like, oh, just go wash your hands with gasoline. Yeah, right? Yeah, my father-in-law tells me to do that all the time. Wash your hands with gasoline, because gasoline is a lot of hydrocarbons. It's very polar, so it can dissolve nonpolar things that water might not be able to do. But I'm a chemist, and I'm very, safety is a core value of mine, so I don't do that. I don't use gasoline. A good alternative is hand sanitizer, because there's some nonpolar components in hand sanitizer that can wash your hands. So do not use gasoline, but if you talk to your grandparents or your parents, they may be like, oh yeah, we did that all the time. We used gasoline. Has anyone done that? Yes? Yeah, okay. But hand sanitizer also works, okay? Okay, good. All right, see, it happens, okay? And it's because of the non-polar qualities in gasoline, lots of straight chain hydrocarbons to dissolve other crud on your hands. All right, next one. This is a ether. I'll just help draw it for you. This molecule looks like water, but instead of hydrogens attached to the oxygens, we just have these carbon groups on it instead. So it's literally, it looks just like water, right, with oxygen in the middle. We just have 2 carbon groups instead. So does it do dispersion? Yes, because it's a molecule. Can it do dipole-dipole? Yes, because that oxygen is bent. Yes, it's polar. It looks just like water. It can dipole-dipole. What about hydrogen bonding? No, it can't. Now that we've replaced those hydrogens on water with carbon groups, those carbons have hydrogens, but they're not directly connected to that oxygen. So no hydrogen bonding. All right, finally, the last one, the black sheep one, NaCl aqueous. So this implies that there's salt and water present. It can do dispersion and it can do ion dipole, all right? Because it's ion from the ionic substance salt, and aqueous implies water is present. That's what's giving us the dipole. Okay, good? Feel good about that? All right. So in this example, we just identified IMFs, but rarely do we ask like, which substance has more IMFs. We usually like to relate it to things you and I can actually measure. So we'll ask questions like, okay, which of these substances has the higher boiling point? So when I ask that, how does that relate to IMFs? This question is really asking what? Which of the pairs has the higher, if I'm asking for boiling point, higher boiling point, we're looking for higher IMFs. Right? Remember, IMFs and boiling point, they relate to one another. Higher boiling point, so we're looking for greater IMFs. Okay, so water or ethanol? Which one has the higher boiling point? So you might want to go through these step by step. Do they both have London dispersion? Yes. Do they both have dipole-dipole? Yes, because that oxygen is in methanol, it's messing it up. Like that oxygen's actually bent, so it's messing up the symmetry. So that has dipole-dipole as well. Can they both hydrogen bond? Yes, so let's focus on the strongest one. Water, how many hydrogens can hydrogen bond? 2 of them, yeah, so this can 2 hydrogen bond, but methanol can only hydrogen bond once. So based upon that, which one has the higher boiling point? Water or the alcohol? Water, yes, because it has doubly the hydrogen bonding capacity. Okay. The next one, trans 1,2-dichloroethene or cis 1,2-dichloroethene. So these 2 molecules are actually isomers. They have the same mass, same molecular weight. Okay. So again, I like to just go through all of them. Do they both have dispersion? Yes. Do they both have dipole-dipole? No, they don't. Yeah, they don't. See how the chlorines are oriented with one another? So this is kind of flashback to chapter 9. All right, so these, so the molecule on the side, if we draw the bond dipoles with chlorines, one's going like 2 o'clock, and then one's going whatever direction that is, like 9 o'clock or, I don't know, 8 o'clock, right? So if you add up these 2 bond dipoles, they cancel. Do you see that? So the trans version of this molecule is what? Polar or nonpolar? Non-polar, yeah. So if you think babies and bodybuilders, you'll just think, oh, those 2 bodybuilders, they cancel out their pools because they're 180 degrees from one another. But what about the cis version? Is that polar or non-polar? That's straight up polar, yeah. So it's polar because there's an overall bond dipole in one direction when you add up all the vectors. So based upon that, which one's going to have the higher boiling point temperature? The trans or cis? Cis, yes, because it's polar. Because this one has dipole-dipole, the other one doesn't. Okay. All right, the last one, Br2 or xenon. Which one has the higher boiling point? So go through the list. Do they both have London dispersion? Yes. Do they both have dipole-dipole? No, they don't. So let's back it up to go back to what they both share. Let's go to London dispersion. When we look at London dispersion, what's our criteria? Mass or surface area. So let's look at the molar masses. Bromine is what? So it's diatomic, so you need to double it. Oh, where's my thing? Oh, I don't have that one either. I didn't know that. What's the molar mass of diatomic bromine? Mirror. There we go. It's like 160, yeah, 160-ish. Remember, it's diatomic. And then xenon is what? 130-ish. So based upon that, which one's going to have the higher boiling point? Bromine. Also, what's the second criteria we use for dispersion? Surface area. Which one has more surface area? The what, Br2, yeah, because it's like a little, like it's a snake, or it's like 2 balls versus like just balls stacking. All right, so for 2 reasons, diatomic bromine has more IMFs present. Also, let's think about it. Bromine is what physical state at room temperature? Liquid. What about xenon? A gas. So let's think about it. If bromine is a liquid, is its boiling point above room temperature or below room temperature? Think about it carefully, because I messed this up too. It's above. Yeah, so if room temperature is like 25, just make up a number in your head. So you're like, okay, boiling point temperature is 100 degrees Celsius. Okay, then that's a liquid at room temperature. So the boiling point temperature is above room temperature for bromine. But xenon is a gas, so its boiling temperature is what? Is it above or below room temperature? It's below, yeah, and so that fits our, observations and our trends that we used here, right? Sometimes you can think your way out of things, right? Yes. All right, how do we feel about that? Good. Rarely do I ask which one has more IMFs. Typically, I relate it to trends. So up until now, we've only really talked about boiling point, all right? We said that as IMFs increase, we say that, okay, boiling point temperature increases, but there's also some other trends we can think about with IMFs. So again, intermolecular forces, it's attractions between molecules in a sample. So I like to think of the more attractions molecules have to one another, the more they're hugging one another. And this will make sense soon because the two trends on this slide are viscosity and surface tension. So the first one's more interesting. Viscosity, it's how slow a liquid flows out of a container. So things that flow slowly are very viscous. They have high viscosity. So if we think about like water flows fairly fast, but honey flows really slow to the point that it might not flow at all if it's stuck at the bottom of your container, right? So viscosity trends with IMFs. The more IMFs that are present in the sample, typically you will observe a higher viscosity. I like to think of it as more IMFs, the particles in the liquid phase are hugging one another, so they're not gonna let their friends like pour out of the jar. Does that make sense? I like to think of it that way. So viscosity trends with IMFs, but it also trends with temperature. So when you increase the temperature of your sample, you heat it up, you give it more kinetic energy, it starts to flow faster. I think we use this in our everyday life. Like I just said, honey has a very high viscosity. It flows very slowly. You ever try to get the honey at the bottom of the jar? Remember, I'm cheap, so I want to get everything. How can you try to get everything out of the bottom of a jar without using a spoon? You do what? Okay, flip it over, but I'm running out of time. I'm running out of time. Heat it up, yes. Someone said, oh, I do that to peanut butter. He microwaves peanut butter. Yeah, I don't know. And I asked him, I said, when you microwave peanut butter, how does the consistency change? And he said, oh, it gets thinner. Right? So you're changing the viscosity when you heat something up because you're giving the sample more kinetic energy. All the friends, they're bouncing around a little bit more, so they're more likely to let go of their friends and let them pour out of the container. So both IMFs and temperature affect viscosity. So I mentioned I'm really cheap, right? So I change my own oil in my car, all right? Except I don't like to do it in the winter, okay? Who changes the oil in their car? No one? Okay, 2 people, 3 or 4 people. Okay, so in the winter, when you change the oil in your car, what do you do before you open your drain plug? You turn on the car. You turn on the car. What does that do? What does that do? It warms it up. So what changes about the oil? Yeah, it makes it not thinner, but it changes the viscosity so it flows out faster. So you're not sitting there all day waiting for it to drip out. So viscosity is actually, has some measurements here, are SAE ratings that you can look at the different oil types in your car. So SAE stands for Society of Automotive Engineers. So their reference points here are high SAE ratings are things that are very viscous, like hydraulic fluid, typically high SAE ratings. Things that are thinner typically have lower SAE rating. So here 10, you see that it's flowing faster. So if you look at the caps, like under your hood of your car, you'll see different oil types for different types of vehicles for that specific engine. So for example, different oil types will be like 0W15 or like 5W20. So those numbers are SAE ratings to tell you how thick, how viscous those different oils are. So a 0W would be a less viscous, so it would flow faster than something that was like 5W. The two numbers are cold crank versus operating viscosity, if you're wondering about that. Okay, so that's viscosity. I think that's more interesting. We use that every day. We heat things up to make it flow easier. All right, and then the other one that's not as interesting is surface tension. So, you look at like a pond of water, you see leaves floating on the water, bugs floating. It's because of high surface tension of water. So surface tension also trends with IMFs, more surface tension of that specific sample. So what surface tension is, the definition, you'll read it once and it won't make sense, but then I'll explain it, then it'll make sense. So it's the net downward force experienced by molecules at the surface of a liquid. So let's pretend to be a water molecule. You are this pink water molecule. You are attracted to other molecules, right? Other water molecules. So if you're in the bulk, meaning in the center of the sample, there is a water molecule above you, below you, to the left, to the right. So do you experience a net attraction in any one direction? No, all of those vectors cancel out. So in the bulk, there's no net force on that one molecule in the center. Where it changes is at the surface. So surface chemistry, it's like its own other world of chemistry because of this fact. When you're at the surface, you have a molecule to your left, to your right, underneath you, but is there one above you? No, there's not. So when you add up all of these vectors, you see that there's this net force pointing downwards. And so surface chemistry, surface phenomena, surface physics is this whole nother field because things behave differently at the surface because of this missing piece above here. And so all of these particles at the very top at the surface have this net force pointing inwards. And so this is why droplets will form spheres because they want to minimize this force. And basically, if the more IMFs that are present in your sample, the larger that missing piece, the larger that downward arrow will be. And so that's why IMFs trend with surface area or surface tension. So water, because it has a high surface or water has a high IMFs, has a fairly high surface tension. So there we go. Those are those two trends. So I could ask any one of these questions, right? I could go back here and be like, okay, which one has the highest boiling point? Which one has the highest surface tension? Which one has the lowest viscosity? All of those are basically asking the same question. You just need to know how the trends are. It all points back to IMFs. Okay, good? All right. Okay. All right, so let's move on. So those are different properties of liquids. Let's talk about phase changes. We've talked a lot about liquids and how the temperature at which a liquid becomes a gas, its boiling point temperature, is typically indicative of the extent of IMFs. So there's a little detail that I've lied to you up until now. You know, boiling water seems as simple as, oh, you heat water from 0 to 100 degrees Celsius, right? That's how you boil water. But no, when we did Q equals MCAT, right? Q equals MCAT. Q is the heat required to change some mass of water with a specific heat times delta T. That's just the energy to heat the water. I can calculate the energy to heat water from 0 degrees to 100 degrees. That's a calculation. But I could have 100-degree liquid water, and that's different than having 100-degree steam water, like gaseous water, all right? So there's this extra piece I haven't told you about. There is an energy requirement to turn liquid water to gaseous water. That's another term that we haven't talked about yet, and that's called enthalpy of vaporization. That the energy required to turn the liquid form into the gaseous form is related to IMFs as well. So the energy to actually separate the molecules from the liquid phase to the gaseous phase. Same thing with turning a solid to a liquid. So all of these phase changes, yes, memorize them. We've talked about a lot of them. Melting, vaporization. Maybe a new one is condensation. It's the same energy value, it's just a different direction. And fusion. Fusion is turning a liquid to a solid. And then new ones here, sublimation, going from a solid to a gas. Deposition is the opposite, gas to a solid here. And so IMFs, as attractions increases, these enthalpy values to change the phase, change how far apart particles are away from one another, typically also increases as well. So just like Hess's law, if we want to go to an energetic system, we have to add energy to the system. It's a positive Q. But if we want to turn a gas to a liquid, that's exothermic. That actually releases a little bit of energy because we're going to a more stable system. So the energy values associated with these phase changes, it's the same value you look up. You just need to use your chemical intuition to know what's the sign. So these two phase changes, vaporization and condensation, they both use delta H of vaporization for that substance, right? Where to vaporize, is that a positive or negative Q value? Do you put energy in or take it out to boil something? In. What about the opposite? Turning a gas to a liquid. I know it's weird, but literally just think of thermochemistry. If you reverse a exo or an endothermic reaction, it becomes exo. Yeah, so turning a gas to a liquid is actually exothermic. All right, that's weird to think about. Or turning a liquid to a solid fusion, that also is an exothermic process as well. All right, so these processes, these are related to delta H of fusion, while our gas and solids are related to delta H of sublimation. We just need to know what the sign is. All right, and the nice thing about Hess's law is that the enthalpy of sublimation, the energy required to turn solid into a gas, is equal to these two enthalpy steps, fusion plus vaporization. All right, because of Hess's law. We can go straight to a gas, or we can take a pit stop at a liquid and then go to gas. All right, so let's talk about how we can use these energy terms. All right, so in chapter 5, we heated a lot of water, right? We heated a lot of water. We used the specific heat of water, all right? To heat water from like 10 to 20 degrees Celsius, what equation did you use? Q equals MCAT, right? Yeah, so to heat water from 10 to 20 degrees Celsius, we would use Q equals MCAT. Q is heat, M is mass of the water, C is the specific heat of water, and delta T is how much the energy change or temperature changes. So those are just energy or temperature changes for a specific sample. Now we're adding this term of enthalpy for changing the phase. These are two different steps. To boil water, I know it sounds as simple as just boiling water, you just heat the thing. But the energy, where it's going, you're first adding energy to the pot of water to heat it, to change its temperature. So you're using Q equals MCAT to turn like 0 degree water to 100 degree water. But once it's at 100 degrees, once your water is at 100 degrees on Earth, does the temperature keep rising? No, water doesn't, no, the boiling point of water is 100 degrees, right? So if you add more energy to the system, all of that energy now starts going to changing the phase. That's when water starts to boil. When we talk about change of the phase, now we use enthalpy of vaporization instead. So let me break this down. Here's a heating curve. This is what I'm talking about. If you just added heat to water, you would see these different temperature changes. So if we started with ice and started heating it, the initial energy would go to heating the ice up to the melting point. Then, once you get to the melting point, all of that energy goes into converting the solid to a liquid. Once we have the liquid, now we use specific heat of the liquid and we heat the water again. And then once we're at the boiling point, all the added heat goes into changing the phase. So we use Q equals MCAT on these blue lines. You already know how to do that. On the blue lines, we are changing the temperature. We just Q equals MCAT it, but be specific here. These lines have slightly different specific heats. So the specific heat for liquid water is our 4.18 number we know and love, but the specific heat for ice, solid water, is a little bit different. It's like 2, so it's a little bit different. And then the specific heat for gaseous water, so steam, is also a different number. It's 2. So there's different energy requirements to heat these numbers. You know how to do the blue parts. You just Q equals MCAT. So these red parts are the energy to change the phase, all right? So at D, we have the liquid. At E, we have the gas. At C, we have the liquid. At B, we have the solid. So to go to B to C, we use the enthalpy of fusion. All of the added energy goes to changing the phase. So these are the red lines, is where we use our vaporization values or our fusion values. So then to go to D to E, we're turning a liquid to a gas, so that is fusion. Or sorry, that's vaporization. So do note here when we are given values, it's 40.7 kilojoules per mole. To change the phase of water, it takes 47 kilojoules of energy to convert 1 mole of water from a liquid to a gas. So note the units here. We have to be in moles versus when we Q equals MCAT, grams is fine. So just be aware of that. All right, so I mentioned here, if we look at the fusion value and the vaporization value, we see that it costs a lot more energy to turn a liquid to a gas than it is to turn a solid into a liquid. So here, vaporization is always greater than delta H of fusion. Why do we think that is? Why does it cost me more energy to turn a liquid to a gas than a solid to a liquid? If we just think about where the particles are, hopefully this explains it. Vaporization, we're turning what? A liquid to a gas. Liquid particles, I don't know, they're all like close together versus in a gas is that. So compare the IMFs being broken in this scenario versus fusion, which is a solid to a liquid when we melt something. So we're turning a solid, which is packed all nicely together, and a liquid, it's still, condensed, not as packed as more, but like, does it take more energy to go from this to this or solid to liquid? Liquid to gas, yes. So this one takes more energy because you're spreading those particles more apart. So that's why vaporization is always a greater value. Always takes more energy to vaporize something because you're separating the particles more versus in the fusion thing. So solid to liquid. Okay, so let's do some calculations because we learned, the blue lines we use Q equals MCAT. The red lines, when we change phase, we use our enthalpies of either vaporization or fusion. So let's do some calculations. This is the last time we'll use our calculator. Right here on this slide. Okay, so how much energy in kilojoules is required to melt 275 grams of solid ice at 0 degrees, so it's melting point, into liquid water? So the idea here is we're turning solid, H2O, to liquid H2O at its melting point. So, do we use Q equals MCAT here? Remember what cat is, or AT, so the delta T. Are we delta T'ing this? Is there a delta T happening? No, it's at 0 degrees. So we don't use Q equals MCAT. We're just going to use the enthalpy value. But which one do we use? Do we use fuse or vape? Fuse or vape? Which one? So solid to liquid. We're using fusion. Solid to liquid. Okay, because vape is liquid to gas. We're not doing that, so we're doing fusion. Use your intuition here. What should the sign of Q be if we're turning a solid to a liquid? It should be positive because we're adding energy. So can I just take this 6 kilojoule number and multiply it by 275? No, units are all messed up. So I need to turn that 275 grams of water into moles. So I'm going to divide by that 18 number grams, 1 mole of water. So that equals something like 15.26 moles of water is present. Right? Now I can multiply by the enthalpy term. So whether it was, if we were melting it or boiling it, we would still need to use this mole number and multiply by the appropriate one. So I'm just going to multiply by the fusion number. So 1 mole requires 6.02 kilojoules of energy, and I know it's a positive number because it takes energy to turn a solid to a liquid. All right, just use your intuition. To melt something, you heat it. You add heat. You're the system. You're adding heat to, you're the surroundings. You're adding heat to the system. Okay. So that's just melting water at its melting point. So let's do a little bit trickier one. How much energy in kilojoules is required to turn the same amount of water, but this time it's at 15 degrees, so it's a liquid, and we want to convert that into steam. Okay, this is like something you would do in your kitchen. You have a 15-degree pot of water. It's 275 grams, and you want to boil it. So when you add heat to that pot of water, initially all of that heat goes into changing the temperature, right, until the boiling point. So the first step here is, like, let's look at the strategy. We want to turn 15-degree water to 100-degree water. What equation do we use? What equation do we use to change the temperature of water? Q equals MCAT. Yes, Q equals MCAT. Do we know M? Yes. Do we know specific heat of water? Yes, we do. Do we know delta T? Yes, it's 85 degrees. Okay, so we know the Q for that step. But when we heat water to 100 degrees Celsius, is it steam yet? No, we need to add more energy to convert the liquid into a gas, into steam. So the next step is, okay, let's turn that 100-degree water into liquid water into 100-degree gaseous water. Do I use Q equals MCAT here? No, there's no delta T happening. So here we use our delta H term. Which one? Vape or fuse? Which one? Vape. We use vape because we're turning a liquid to a gas. And so I already gave you that number, so we're using the other one over here. All right? And so be cognizant here, which specific heat do we use? The 4 or the 1.9? The 4, yeah, so make sure you're using the right constants for the right phase. All right, so we actually have to do the calculations for these steps separately, and we're gonna just add them up here at the end. So Q equals MCAT, so the Q step for heating, that's what I like to think of as just like heating, the delta T part. Q equals the mass, so 275 grams, times specific heat, 4.184, times delta T, so 85 degrees Celsius. All right, and so you get something like it's 97,000 joules. All right, so I just want to convert that to kilojoules, so it's 97.8 kilojoules. That's how much energy it takes to just heat the water from 15 to 100 degrees. Liquid water. We need to add additional energy to actually boil it. So this is where we use our delta H of vaporization. So I'm not going to use the gram amount. I'm just going to reuse that 15.26 mole amount that I got before. That's how much water we have, and we're multiplying by 40.7 kilojoules. So that's how much it takes for 1 mole of water to be converted from a liquid to a gas at its boiling point. So if you calculate that, you see that just the boiling part, converting the converting the phase of the water, requires 600 kilojoules of energy. All right, so it's both of those steps we need to add up. That's the total amount of energy it takes for this entire process to happen. So when you add up these two numbers, you get that 700 number. All right, so we have to do it in 2 steps: heating the water, boiling the water. So if I go back, let me just go back, you write that down. If I go back to this slide, all right, so what we basically did is we started here, right? That's my 15-degree water. We calculated, okay, how much Q is required to heat it from 15 to 100 degrees, and then we calculated, okay, how much does it cost me to turn it from a liquid to a gas? So this amount of Q is what we just calculated, all of those steps, to change the temperature to the boiling point and then to boil it. And so you can imagine it's just more calculations if we wanted to start from A and go all the way to F. And I think I have you do that in recitation, right? It's just different steps. For all the blue lines, you use Q equals MCAT. For the red lines, you just use the phase change, appropriate phase change. All right, so that's how you boil water. That's how you boil water. All right, so, oh yeah. Okay, speaking of that. Okay, so water, to boil water, we have to get water to 100 degrees Celsius, right? You agree with me? Okay. When you boil water, you turn what into what? A liquid to a gas. Very good. All right. So you tell me, are these children in these pictures, are they in danger? They're on top of these puddles. We know puddles evaporate, Evaporation is what? Liquid to a gas. But you just told me that water boils at 100 degrees. Are these children in danger? No, our intuition tells us no, but your chemistry mind is going, what the heck is happening? They're not in danger, but yeah, water boils at 100 degrees. Why are they safe? There's a new aspect I didn't tell you about that explains evaporation, all right? So yes, when we boil something, it turns a liquid to a gas, but that's not the only way we can turn a liquid to a gas. It's not only at the boiling point. Things like if you leave a cup of water on your nightstand for a long time, as long as the cats don't drink it, we know that eventually all of that water evaporates. We know that our nightstand isn't at 100 degrees Celsius, but it happens slowly over time anyway. And that's due to an idea, a new one called vapor pressure. So in order for a liquid to turn to the gas phase, a liquid to a gas, two criteria need to be met. First, the kinetic energy of your particle needs to be greater than the IMFs, the attractions holding that particle in. Also, that particle needs to overcome external pressures that are being exerted on that sample. So these ideas will come up. All right, so evaporation is explained by vapor pressure. Vapor pressure, if you have a vat of a liquid, if you have a liquid, okay, and you stick your nose above the liquid and you sniff really hard, you might be able to send some of those liquid particles into the gas phase and enter your nose. You might even be able to smell the liquid, all right? So some liquids exert higher vapor pressures than others. So for example, if you sniff water, does it smell like anything? No, not really. But if you sniff acetone, nail polish remover, does it smell like something? Yes, it does. So, but the thing is, like, when you are, doing your like nail polish or whatever, working with acetone, is it boiling? Are you sending gas particles into the atmosphere? No, but you still smell it. You still smell the gas particles, but that's because that sample is exerting a high vapor pressure. So where this comes from, it's the idea of if you looked at all of the kinetic energies and of all of the particles in a liquid sample, they're not all moving at the same velocity. Some of the particles will have enough energy to escape the liquid. Some of them do. If there's the temperature of the sample is higher, then maybe more of those particles will escape to the gas phase. And this is all below the boiling point temperature. So the idea is if you increase the temperature, you kind of adjust where that average kinetic energy is, allowing more particles to escape. So the trends you want to see here is as your IMFs in your sample increase, vapor pressure actually decreases. So this one's a little bit different. So I like to think of it, again, IMFs in your sample, it's like your particles are hugging one another. So if your particles are hugging one another, are you going to let your friends escape into the gas phase? No, you won't. You won't let them. All right, so that's why the vapor pressure is low for samples that have high IMFs, because they're all hugging one another. They're not letting their friends go into the gas phase. If you increase the temperature of your sample, you're giving everyone a little bit like more juice, and they're all like wiggling around. Okay, if they're all wiggling around, they're not hugging each other as much, so they'll let their friends go into the gas phase. So that's why vapor pressure increases as your temperature of your sample increases. Okay, vapor pressure, this is hard to explain. I like to use intuition here. So just agree with me that a sample will exert a high vapor pressure typically when it smells, like it's smelly, when you can smell it. So like I said before, which one, based upon that idea, smelly things have high vapor pressures. Which one has a higher vapor pressure at room temperature, water or acetone? Acetone has a higher vapor pressure because it smells, yes. Some people are like, oh, it smells good. Not if you smell it all the time. Okay, so based upon that, remember our trends, that as IMFs increases, vapor pressure decreases. So based upon our ideas here, which one has stronger IMFs? Water, yes. Let's check our work. Water, what's its strongest IMF? Hydrogen bond, what's acetone's strongest IMF? Dipole, dipole. So that tracks, it tracks. Okay, cool. All right, has anyone ever made pickles? Homegrown pickle, you take cucumbers, you put it in vinegar. You ever like boil vinegar? No? Yeah? Yeah, boiled vinegar. Just for the people who haven't. You know what vinegar smells like, right? Imagine you boil it. Do you think the smell is gonna get more intense or less intense? More intense, and that has to do with adding kinetic energy to the sample. Vapor pressure increases. So the smelliness of hot vinegar is a consequence of that increased vapor pressure. So yeah, heated vinegar. Okay, there we go. All right, so and so here are all the trends for vapor pressure. So vapor pressure, when you have a liquid, this is the number of gas particles directly over the liquid. So if you're in a closed container, you can actually measure the vapor pressure being exerted here if you have your solution or your substance in a closed container. So I like to write here, vapor pressure of your sample when we're making comparisons, it's temperature dependent. All right, higher temperature, more vapor pressure. It's also dependent on the IMFs that are present in your sample, so it depends on the identity of your sample. All right, and again, there's those trends. All right, so some misconceptions here. Vapor pressure, and you'll talk more about this in 1220, is not dependent on the volume of the container or how much of the liquid you have. You can try this for yourself if you have like a big, a cup of acetone versus like a small thimble of acetone. If you stick your nose in it, they're probably going to smell equally as bad, right? Whether you have a large amount or a small amount. The vapor pressure above that liquid, as long as they're at the same temperature, are the same. Okay, so, and this is a big part of 1220 that you'll talk about. So I mentioned vapor pressure. As you increase the if you increase the temperature of your sample, vapor pressure increases, okay? So why vapor pressure is related to boiling is you can increase the vapor pressure so much in water, let's say, so much that once the vapor pressure equals the external pressure on your liquid, that's when your substance will boil. When your vapor pressure is equal to your external pressure. On Earth, what is your external pressure on a pot of water? 1 atm. Yeah, so once your vapor pressure of water is equal to 1 atm, that's when your substance will boil. The temperature at which vapor pressure equals 1 atm is different for all liquids depending on the IMFs present. All right, so here's a pressure curve for water, and I wanted to show you a demo here. Again, any substance, any pure substance will boil when your vapor pressure equals your external pressure. So for water on Earth, at 1 atm, its vapor pressure equals 1 atm at 100 degrees Celsius. That's why water boils at 100 degrees Celsius. But remember this boy? What's this boy? Oh, this is his big brother, sorry. This is a big vacuum pump. What can I do in here? I can reduce the pressure inside this bell jar, right? So if I tried to boil this water right here on Earth, what temperature would I have to get it at? 100 degrees, yes. So right now this water is at 19 degrees, all right? It's like, it's going down, 19 degrees, all right? So I can change the pressure surrounding this water by using my vacuum pump. And we'll see what happens. There's a common misconception when things boil. When you see something boiling, typically you think it's hot. Yeah? So I just proved to you that this water is at 20 degrees Celsius. It's like pretty cold. It's cold water. So I'm going to turn this on, and we'll see what happens. This takes a little bit of time. All right? So we'll just see what happens. Okay? So what I'm doing is reducing the pressure, because the idea here is if I reduce the pressure along surrounding the external pressure around that water, perhaps the kinetic energy that's inside already at that temperature, at 20 degrees, will be enough where this will be true, that the vapor pressure being exerted on that water at 20 degrees Celsius will equal the external pressure being there. So let's see if that happens. It's not happening quite yet. All right, it's not happening. The bubbles that you're seeing is just the oxygen leaving the water. All right, so this is why, and also an explanation for why pressure cookers and low altitude boiling instructions are often there. Okay, there we go. See, does that look like it's boiling? Does that look like it's boiling? Yeah? Okay, and what's the common misconception we have? When things boil, it's hot. So like your brain might be thinking, oh yeah, that's hot. That's hot. But I promise you, it's not. So it's boiling, right? So I'm gonna just take this out. Okay. Okay, you just saw it boiling, right? It was like rolling, boiling, and I'm just gonna, it's straight up cold, all right? So you can touch it if you want before you leave. It's straight up cold, okay? Because there's different ways to boil things. Yes, we can heat it, so its vapor pressure becomes 1 atm, but if I reduce the pressure surrounding it, I can also achieve the same thing. So it is straight up cold. Oh crap, we didn't finish it. Okay, I guess then homework is due. Okay. Whatever. Well then, yeah. Dang it.